Hello, so I am Joao Santos and from CELIA at University of Bordeaux in France, and I am here with our team in collaboration with CLPU and other international collaborators to perform an experiment of intense laser interaction with quasi-critical gas targets. So what is quasi-critical? It means it's a density that is at the limit of propagation for the laser pulses. And this density is brought by high pressurized gas jets, which are a kind of target that in principle would become compatible with a high repetition rate use. And why high repetition rate is interesting? Because for many applications, including plasma physics, which is our main field, but also other multidisciplinary applications like radiobiology or even medicine or nuclear physics, need high dose of accelerated particles. So that's why the high repetition rate is important. So this is quite exploratory because these kind of targets have been developed only through the last 5 years maybe, and moreover their use in the harsh conditions of petawatt laser interaction are remain quite unknown. So we have been through solving a series of technical difficulties, like how to maintain vacuum in a chamber where you are puffing gas jets constantly, and how to make the system that opens and closes the valve survive the intense electromagnetic pulse that are emitted every time that an intense laser interacts with matter.
Hello, my name is Valeria Ospina Borges. I'm a third-year PhD student in the group of Joao Santos at the University of Bordeaux. My PhD is also sponsored by CA-DAM, and I'm in co-tutel with the University of Salamanca. And I center my PhD studies in the ion acceleration from near-critical gas jet targets. Basically, laser interaction has mainly been studied in solid targets, but if we enter in regimes where the density of the target is reduced enough to let the laser propagate through this target and at the same time couple strongly with the electrons and give a lot of its energy to the electrons, we can arrive to very high volumetric heatings of this target, which can then trigger what we know as collisionless electrostatic shocks inside of these transparent, very heated plasmas. And these electrostatic shocks, given the correct conditions, can then propagate and reflect background ions, accelerating them to very high velocities in a monoenergetic way, as it's expected from the numerical study that I have performed so far during my PhD. So here in this experiment in the Vega 3 Betawatt facility of CLPU, we are trying to study precisely these interaction conditions and to find hints of this regime and of this type of interaction and acceleration. And we are very, very excited to see the results of this experiment and to advance a bit more in this research field.